All right. Got number one. You should have gotten number one. All you had to do was read that average atomic mass spectrum, and you're looking at the percentage. And if you look at the average atomic mass for each isotope, is going to be your mass number up there. They don't give you anything else. So to find your average atomic mass, you're going to multiply your percentage times the mass number, and then you're going to just add those numbers up together. It's a weighted average. So if you didn't get that answer, you might want to jot that answer down. 20.197 is what I got.
179.
179, thank you. I said it backwards, didn't I? 20.179, and then you're good to go with that.
If it's average, why don't we divide by 2?
Because it's a weighted average, Tyler, it's kind of like your grades. Your grades are 70% of your grade is content and critical thinking, 10% is communication, and so on. So you don't just add up all your scores and divide by how many you have. You have to multiply, or the computer does it for you, but you take the total points in that category and multiply it by the percent, and then just add them together. That's how you find a weighted average. Because if you think about this, the average atomic mass is going to be based on which isotope is in most abundant, is the most abundant isotope. So the average atomic mass should be closest to the one that's got the greatest percent abundance. And notice that when we find our average atomic mass is 20.179, the one that was in the greatest percentage was the one that weighed 20, right? So this 0.179 reflects the smaller percentages of the other two. Does that answer your question on that? Okay. All right. The next part, we hadn't really reviewed on this, but let's talk about what these series mean so you can do some understanding on this. If you need to know a little bit about the spectrums, okay? I forgot to turn it off. Okay, sorry about that, guys. Let me turn that off. I'm just trying to make sure it didn't continue going off. There we go. Okay, done. So if you look at all of these energy levels, let's think this through, okay? Whenever you get closer and closer to the nucleus, it's going to require more energy to remove an electron, right? So this series of energy spectral lines would represent a wavelength of light that would have the most energy. So that's why I labeled this one ultraviolet. So ultraviolet, and then if you go into more energy, you're talking X-rays, you're talking gamma rays, if you're moving on down that spectrum. So we would continue on this end. Y'all understand what I'm saying? If you're dealing with higher energy. So you notice on the y-axis right here that says energy. So the greater amount of energy would represent ultraviolet. The lesser amount of energy would be infrared. Think about the two extreme, or not necessarily extremes, but the two areas past visible. You can go into the infrared region, which is going to be lower energy, or you can go into the UV spectrum. Think for us as humans, which is more dangerous to us, to our skin? Ultraviolet? Yes, ultraviolet definitely is more dangerous to our skin. They say protect yourself, wear sunscreen so that you're not getting possible cancer later on in life. And so the visible spectrum, if you didn't know this, should be these two middle ones. Did anybody look this up to contradict what I'm telling you? So you could have looked that up. That's why I think I said look some of these up if you need to. Okay, just to figure those out. Okay, so then the question that asks, it says the emission spectrum for the series are in IR, visible, and UV. Match the series with the region and justify your choice. So the reason that we would match those up would have to do with energy. So UV is going to have the most energy, and you can see that represented in the graph. And infrared would have the least amount of energy, and so that's why it's on the other end. And then the visible spectrum is actually the Balmer and the Paschen series. Okay, ignore this part about IB because we're not IB, we're AP. Okay, and then B says, would the wavelength of light be longer or shorter for lithium for an n equals 2 to an n equals 1 transition than it would be for hydrogen, and then justify your answer. Okay, which one is farther away from the nucleus for lithium versus hydrogen? Lithium would be a little bit farther away from the nucleus. Hydrogen is going to be a little bit closer to the nucleus. Okay, question on that? Okay, so lithium has 2 energy levels, right? Hydrogen only has 1 energy level, correct? Okay, so let's think about what's in the nucleus for each one. You've got little hydrogen has 1 proton, correct? And it's got 1 electron. And here it is. What energy level is that electron in? Energy level 1, 1s. So it's in that 1s orbital, okay? For lithium, you've got 1, 2, 3 protons in the nucleus, okay? You've got energy level 1, Eli. Energy level 1, which has how many electrons in it? 2 electrons. Energy level 2 has how many electrons in it? It has 1, okay? All right. Now, if you have, you make this electron jump out to a higher energy level there for hydrogen. So it's going out to energy level 2. What's pulling that electron back in? That one little nucleus, right? And so first of all, one thing to understand is this electron is going to be a little bit closer to the nucleus than, well, these actually are going to be pretty close to the nucleus because you've got 3 protons versus 2 electrons. So they're going to be pretty tied in. And then this 1 electron is going to be farther out here, okay? Because you've got these 2 electrons that are doing some repelling shielding. They're keeping that 1 electron from gaining access to the nucleus. So if you've heard that term shielding before, that's what shielding is. It's those inner electrons that are repelling the outer electrons, keeping them from access to the nucleus. So you have to think about the distance between here to here, which distance is going to be greater. And so you're going out here from, this is energy level 2, back to energy level 1. And here, energy level 2 would probably be just right here real close because you don't have anything that's keeping this electron from bumping out here. There's not another electron in there. So these 2 energy levels are going to be pretty close to each other. These 2 energy levels are going to have a little bit more distance between each other, okay? Because there's repelling force from those 2 electrons that are between that 1 electron. So you have to think about which one is going to require more energy or is going to, whenever they fall back, they don't require energy. What do they do with the energy? They release the energy in the form of visible light. So the question says, would the wavelength of light be longer or shorter for lithium? Okay, so the shorter the wavelength, the greater the energy. That's right. So that's one of the things you need to make sure that you get in your head. It's an inversely proportional relationship. The shorter the wavelength, the higher the energy. The longer the wavelength, the lower the energy. Okay, so if you've got something that required more energy to make that jump from N1 to N2 and then it falls back, okay, and why did it require more energy in the first place? Because you're trying to pull it away from these 3 protons in the nucleus versus having to pull it away from 1 proton in the nucleus. Does that make sense on that part? Okay, the pull is greater, so it takes more energy to make it make that jump. So whenever it releases that energy that it took to make the jump from N1 to N2, then it's going to release the same amount of energy that it took to get out there. And so that amount of energy is going to be greater. Therefore, it's going to be a shorter wavelength. Okay, some of you are nodding your heads.
It's shorter because it releases more energy.
That's right. That's right. And it all has to do, on this part, guys, with proton to electron ratio. Okay? And how many protons are pulling in on those electrons that are trying to make energy level jumps? The more protons you have that are pulling those electrons in, the more energy is going to be required to make that jump. Okay? And we're talking like N1 to N2. We're not talking way out there. We're talking N1 to N2.
It's not N1 to N5.
Right, exactly. Yeah. But still, if you're going from N1 to N5, and think about how close N1, energy level 1, is to the nucleus. And if you have a whole bunch of protons in the nucleus, isn't going to require a lot of energy to make it out to energy level 5?
Yep.
Yeah. Okay. So you're trying to get that little electron that's in energy level 1 all the way out to energy level 5. If you've got a nucleus that has like 32 protons in it, it's going to require more energy than it would if you have a nucleus that only has 3 protons in it. Okay. That makes some sense on that part. Okay. So always think about, these are just like magnets. Okay. And Yibo, who else? Wyatt, Cab. Is that all? Alex. All right. You saw that?
I'm confused. What?
Coulomb's law. This is all about Coulomb's law, what we're talking about today. You weren't in at that point? Yeah. That was one of the ones y'all missed. So it's like, no. Yeah. It was like a name, but they said scientific laws. And so they gave that definition, and it was Coulomb's law. Did you remember that one?
Was that cold? What?
And were you on the panel at that point, Alex?
On
Quizbowl, yeah, on Quizbowl, Alex.
I don't
Yeah.
remember that.
You don't remember Coulomb's law? You don't remember?
I don't remember all the questions.
I gotcha. I only remember the chemistry ones. So, because I was like, no, they know Coulomb's law. And then Graham's law and Dalton's law were the other two that was like, what? And had Sydney and Patrick been in class on Friday, they should have gotten Dalton's law, because that's the exact law that we talked about on Friday was Dalton. But all my AP students, come on.
They were letting you down.
Oh, no, it's okay. Y'all got the other ones right. The only one that really like broke my heart was when Patrick said electrode. Was it Patrick that said that instead of cathode?
Yeah, that was wrong.
Oh, was it Cannon? Okay, yeah. So what? No, not electrode. It's cathode. Y'all know this. Red cat.
Electrode is more general.
Right. And it was asking about that was in the question. Which electrode does reduction take place at? Electrode. Yeah. I know you're under pressure, but you guys did good. Congratulations, by the way.
Thank you.
Congratulations. And if I think I put out congratulations, Yibo. You did a good job, man, on that physical separations lab. You got second place out of everybody that was in there. So good job, man. Nicely done. I have to look at my email. I don't remember, but anyway.
Hopefully, like,
It was Lake Hamilton, I think. Yeah, Lake Hamilton. They were. Yeah. It wasn't Owen. It was Lake Hamilton. Okay, so guys, let's move on away from the atom. Okay. Do we have the ideas of the atom down on this? Because this is kind of some study notes. You might want to write Coulomb's law down. Coulomb's law is force is proportional or equivalent to, should we say, that's why the little fish is there, Q positive, which is charge, times Q negative over distance squared. I can put it up here, so you don't have to squint to find it. Okay, so use Coulomb's law to help you defend anything that has to do with charges. Whoops, Q, that's supposed to be a Q. Positive. Absolutely. Anything that is anything. I know, right? No, so that's why I've been saying study. Yes. Yeah, it's going to be like your AP exam, like the big thing. Yeah, to get you. It's like one last push. So hopefully you guys do some studying. Okay. If anybody wants one of those books to use, I've got some. So okay. So before you leave class today, grab one from me. It's a AP study book. Yeah, probably want to grab that, Casey. After the test. Don't you bring it back before. I'm talking about after next Thursday. Yeah, after next Thursday. So don't bring, well, you could technically, I guess, no, because in my mind, you are studying Wednesday night next week. You're going to be studying. Okay. So don't need to bring your book back till reduction at the cathode.
Action one.
at the cathode. You remember red cat and ox from electrochem?
I think I just remembered where they were.
Okay, I got you. All right, let's move on through this. Bondings, IMFs. Any questions on these questions? This was now I'm asking, so you guys got to speak up if you have questions on this. Okay, did you label attractive, repulsive on these sides of the graph? Okay, this little graph that you see here, we worked with this. It's been a long time ago, but we used one of the FET things, and we took two atoms and we pulled them apart from each other and got them closer together, and we saw this little graph happen. Okay, it's been a while since we did this, but the attractive forces would be on this side of the graph. They're most attracted right here at the bottom. That's where they're going to be bonded. Okay, so bonding is happening right here. Two things will bond whenever they have the lowest potential energy. That's when they're going to bond. And then the repulsive forces, as you move them farther and farther away from each other, then they're going to be repelling one another. And so the repulsive forces would be here, attractive over here. The main thing you need to get from this graph is the bottom of that is where the distance between, I don't know why that just did that, the distance between the two atoms themselves. And so they maximize their distance right here. They maximize or they lower their potential energy. Actually, what did you say, the horizontal axis? Yes, that would be distance. And then the vertical axis would represent potential energy. PE versus distance.
So
We good? Okay.
Why did you draw that triple?
Because it says on C, draw and label a curve that shows what would change if a bond is a triple bond as opposed to a single bond. So a triple bond will have an even lower potential energy. Okay, yeah, and that's why it's harder to break triple bond, because you've got more electrons in there, and it also causes a much lower potential energy.
So that distance thing, what is the distance between?
As they get farther away from each other. Actually, I think I have this. This needs to be flipped. This is repulsive. I was trying to do this while I was in the hospital with my dad, and this is attractive.
I thought I had gotten that.
I think so. If we think about that, if you get them too close to each other, what are electrons and electrons gonna do to each other? They're gonna repel. If you get the nuclei too close to each other, the protons and protons are gonna repel. So that's why this side, this represents distance, like you said, Yibo. So we get them too close to each other and they're repelling. We get them the perfect distance from each other and they're going to be attracted to each other. So it said to label which side was repulsive, which side was attractive. So really, honestly, the best place is going to be that we could label that as the most attractive place here. But if you wanted to label each side of the graph, your repulsive forces would be here. Your attractive forces would be more over here on this side. Okay.
So this is representing atoms. This curve.
Mm-hmm. Let me show you something real quick before I'll pull it up so you guys can see what I'm talking about. He is doing awesome. Thank you for asking. I hadn't talked to him this morning, but we got him home last night, and he's he's a trooper. He's doing good.
Well, that's good.
I'm proud of him. It's taken him years and years to decide he was going to get this done, but
What did he get done?
he got knee replacement surgery done. So yeah, it's a big deal. Yeah, it's and he has a lot of medical conditions. He has he's 74. So yeah. All right, let's see. Let me pull this up. I already had this pulled up. This is the one we want. Yeah. All right, so I'm going to show you guys this real quick so you can understand it. Eli, you staying with me, sir? You are? Awesome. what I want you to look at as soon as this gets loaded is I want you to look at, okay, so here are two atoms, and notice that as we can turn on the forces so we can make sure. Do you remember seeing this little thing? We never played with this. Shame on me. Okay, so I've got the forces turned on. Now, what is happening right now? Those are attractive forces, but as I get them too close to each other, notice what's taken over. The repulsive forces. Okay, now would you say, Jenna, would you click our lights there so we can see this better? Can y'all see that a little bit better?
So they're attracted until they're too close.
Right, they're attracted until they're too close, and if they get too close, they're repelling one another. Okay, now they're bonded right now. One of the questions that talks about this, it says, why is the distance called the average bond distance? Can you see why this would be called the average bond distance? What are they doing in that bond?
Going back.
That's right. That's exactly right. That's what's happening. Okay, so they're bonded, but they're sitting there doing kind of a vibrational sort of thing. You've got electrons that are moving around each other. Okay. And when the attractive and repulsive forces have kind of reached an equilibrium here, but as they get too close to each other, they're repelling, but they're still attracted. Proton to electrons are attracted to each other.
So this, what we're seeing right now is that where you wrote bonding.
That's right. That's right. Let me show you one. Oxygen has a double bond, and notice what happened to the dip. You can't even see it. I think I would have to zoom out so we can see that on the graph. Do you see what happened right there?
Whoa.
It went really, really, really far down. Okay, and I can kind of make these move a little bit, but you can see that's what they're doing in the bond themselves. They're still bonding, but they're actually vibrating in a position where you've got the repulsive and attractive forces are balancing each other. Okay, now we can check out what happens when you have, here's neon, here's argon. Notice that we didn't really change the potential energy, the distance between the atoms. In fact, I think we actually, let's kind of compare apples to apples here. So neon versus argon. Argon has a little bit more of a potential energy drop. Why do you think argon is going to have maybe a greater potential energy drop than neon does? Has a bigger mass? Well, remember, attractive forces don't have anything to do with mass necessarily. It's all about positive versus negatives. So what does argon have more of? Electrons and protons. So it's going to have greater attractive forces. So that's why it'll have greater repulsive forces, but the balance of their attractive and the repulsive forces is what causes the lower potential energy there. Right. And so you see with oxygen, wow, it's got a double bond in between there, and you get a really big drop in potential energy. Okay. And then neon to argon, we could look at those. Neon to oxygen, they're about the same size. Argon to oxygen. And if we wanted to do a custom attraction, we could, but just kind of see what that whole graph was talking about. Okay. So bonding, and then they're not bonded because they're repelling. They repelled so much that, yeah, they weren't bonded anymore. So like you push them too far in, notice the repelling forces are going to overcome the attractive forces. So it just like pushes it away. Okay. All right. We good on that. Let's move on because we don't have time to continue on that one forever. Okay. So looking at this top graph, okay, let's think about what's going on with each one of these. I've got nitrogen labeled as the lowest one because nitrogen has a triple bond, okay? One easy way to remember that nitrogen has a triple bond is its charge. What charge does nitrogen have when it forms a charge? -3, right? Okay, so everybody look at that periodic table over there on the board. I want you to get a visual image of what can happen with things in nitrogen's group can form triple bonds. Do you see the 3 little lines I have above the nitrogen's group? Yeah. Means those can form triple bonds. The nitrogen molecule is going to have a triple bond. In oxygen's group, notice that you've got a -2 would be the charge. Oxygen in everything in its group could form double bonds. Okay, now I have the little double line, and then the halogens, fluorine through iodine, are going to only form single bonds. Okay, why? They only have one available space for bonding. They have 7 valence electrons, so there's one empty space that they could have bonding happening. And that's what they do. They just form one bond. So if we look at this little bonding curve, I've got nitrogen marked as the one that has the lowest dip. Okay, and let's see if I've done these other two correctly. Based on what we just saw, I think I needed to flip a couple. Do you think iodine or chlorine is going to have lower potential energy based on the simulation that we just saw? Chlorine, I've got chlorine marked as having a lower potential energy, but I believe we need to flip it. Let's talk about why. Iodine has more electrons, chlorine has fewer electrons and protons, so the potential energy should dip more for iodine because it's going to have more attractive forces than chlorine would have. Even though it's a bigger atom, it's still going to have more attractive forces because it's got more protons and more electrons. That's right. That's right. So I needed to flip those two. Okay, so more electrons, protons, then the more attracted it's going to be. Now, there is a distance issue with these two, which is why I originally had them flipped. I was thinking, well, chlorine's going to be able to fit tighter between them, so it should have a lower potential energy. But this goes back to chlorine. It's got way fewer protons and electrons than iodine does. So iodine is actually going to have a lower potential energy, okay? Chlorine will be the smaller, obviously. It's a smaller atom, and so it's going to be able to, you can talk about bond length. The bond length of chlorine would actually be shorter than the bond length of iodine because iodine's way bigger, okay? The bigger the atoms, the bond length is going to get bigger. And another thing, I've had this up here, looks like somebody broke my rubber band or something happened here, but that was representing a single bond versus a double bond versus a triple bond. And the single bond the other day was way down here. Okay, so longer bond length with single, double pulls the atoms in tighter, and triple really gets them close together. Okay, so think about what you just saw with oxygen on there. The oxygen was really, really close, but the repulsive forces were huge, were they not? As were the attractive forces. But you couldn't even see the arrows on the simulation on that one. Okay, letter C, it says, which requires energy? Now this one, guys, we hopefully know, which requires energy, bond formation or bond breaking? Bond breaking. And it's just like, well, you got to break something, so it's going to require energy. You have to get the atoms away from each other, so you have to overcome the attractive forces. Well, if you look at your proton to electron ratio, I think is what's going to happen. So you've got D would be distance. You're right, Yibo. So let's go back to Coulomb's law here and just think this through. But our charge issue, iodine, you've got 53 positives times 53 negatives on top. And then we would have to look at the distance. Yeah, iodine is actually a bigger, you've got greater distance, so that's going to be a larger number than it would be for the other one. But it's the number on top. Look at chlorine. You're 17 times 17. 17 positive times 17 negative. Versus your distance is going to be smaller, so that's going to be a lower number. So I think it's because there's just such a huge, like, look at your two values here, 17 versus 53. I would really want to look at real data on that, but I feel like this greater charge is going to take over. And I'm basing this off of, let's go back, our simulation here. If we compare neon, let's make this, I think that's about as big as I can get that. Neon to argon, watch the dip. Do you see how it actually, can you see that graph? I'm not sure if you can see it. Look at, can you see this part right here? Yeah, okay, watch that. There's neon. Do you see argon? It has a lower dip. So let's double check and make sure I have these smarts right. So we're saying iodine would have a lower dip than chlorine based on the way greater number of electrons. Because look at, like neon to argon, they're just 1 period away from each other. Chlorine to iodine, they're like 2 periods away from each other. So I think there is going to be that the distance part is not going to override the charge part on that. My thought process originally thought the same as what you're thinking, Nebo. Okay, moving on. D says, what is the bond energy in joules for 1 molecule of nitrogen? So if we look at nitrogen, read the graph, I got about 930 kilojoules per mole. This is a unit issue, okay, because look at what it says, the bond energy in joules for 1 molecule. So kilojoules per mole. And then there are 6.02 times 10 to the 23rd molecules in a mole. And then when you get your answer, that's not going to be in joules, that's going to be in kilojoules. So then you would need to convert that to joules. And I did not have a scientific calculator, so you might want to check my mental math on that one. Don't write that down as, well, I had my phone calculator, yeah. But I couldn't put in the exponent part on my phone calculator, even though it looked like I could. It's like, no, that's not the right answer. So I just had to do when you divide something that has times 10, what do you do with the exponents? Subtract them. So that's what I had to do. So if you take 930 divided by 6.02 times 10 to the 23rd, I got this number. And then I put it in correct scientific notation. So that should be 1.51 times 10 to the negative 21st. And Sawyer, are you checking my math on that? 1.54. Not 1.51. Sorry. Say again.
You had one. Oh, that's one.
This was doing this without a well, I just divided 930 by 6.02 and I got 154. And then notice that, I need to double check that. You know what? I don't think that's right. Because I think this would be times 10 to the 20. Yeah, check my math, Sawyer. Are you checking my math? So I think this would be times 10 to the 21st right there. Because 930, if you put that in scientific notation, that'd be 9.3 times 10 to the second. 2 minus 23 would be a negative 21, would it not? Is you're subtracting exponents there? What are you getting, Sawyer, when you divide these two numbers?
Negative 1.54 times 10 to the negative 21st.
Okay, so I did it right here then. Okay, never mind. Get that one. Which way? Up. I'm sorry. Mari, let's see if I can help you out there. Is that better? Okay. I know there's a whole bunch of chicken scratch on here.
So it is 1.54 times 10
To the negative 21st kilojoules.
joules.
And then you're going to divide that by 1,000, right? So when we divide that by 1,000, then we would have a negative 18, I think. Okay. All right. And that's in joules. What does the negative represent? Why is it negative?
Because you're losing.
You're losing energy because energy would be exiting.
Well, this shows that you have a lower. I don't know.
Okay.
You're getting closer.
And bond energy, I guess, by definition, is the amount of energy that is released when 1 mole of this is put together. Okay, so energy is released in the bond making process. Everybody good with that? You got that part down in your head? You break a bond, it's endothermic. You make a bond, that's exothermic. Energy is released. Okay, moving on, guys. This is all about LDFs, dipole-dipole, London dispersion. I already said LDFs. hydrogen bonding, okay? So on number 3, the graph below shows the effect of changing temperature on the vapor pressure for 2 liquids. Ethane is shown and water. So you had to pick which one was ethane and which one was water. So I chose water to be this one. Why do you think I made water this one and not the other one?
It has hydrogen bond.
It has hydrogen bonding, that's right. So it's going to take more, it's going to be hotter whenever it changes over into a gas. That's right. So it's going to take longer for it to become a gas since molecules don't want to separate from each other. Okay, and so there are more particles becoming gases is what I have for A. It says explain why the vapor pressure increases as with increasing temperature, because as you increase temperature, you're increasing their kinetic energy. And so more particles are becoming gases, therefore the vapor pressure would increase. Vapor pressure is just the pressure right above the liquid caused from molecules becoming gases, okay? Then you had to identify the intermolecular forces for each substance. So ethane, just LDFs. Water would have London dispersion, dipole-dipole, and hydrogen bonding. Indicate which curve is likely water, which one's ethane. We already talked about that. Justify your answer using IMFs, and you guys already said that. Sketch the curve you would expect for ethanol, shown below. So here's your little ethanol molecule, okay? And so now if we think about water, water is this molecule. Water's got really, really, really strong hydrogen bonding. Compared to this molecule, would you expect it to have stronger or weaker hydrogen bonding? It's definitely going to have hydrogen bonding, but notice this end of the molecule on the left-hand side is going to be more of a non-polar end, is it not? And so your polar end is just right here. And so you've got probably it's definitely going to fit. It's not going to have forces as strong as water, and it's going to have forces that are weaker than ethane because ethane is completely nonpolar. So I stuck it in between the two, a little bit closer to water than ethane because it does exhibit hydrogen bonding. So does that make sense?
Mm-hmm.
Okay, everybody have that one filled out?
Yep.
All right, moving on then. All right. Number 4, again, we're talking about intermolecular forces. Explain the general increasing trend due to intermolecular forces. And so if you think about what's happening, ignoring those on this side, what do you see as the general trend for all of those groups? They're increasing. Now you've got some anomalies there, okay? So you've got NH3, water, and HF. And so you had to explain what's going on with those. So what do those 3 things have that the rest of them don't exhibit? Hydrogen bonding. So these all have hydrogen bonding, which is the strongest intermolecular force, which is why you see that blip in the graph. Okay. All right. And then D says, why doesn't CH4 follow the same pattern? Because it doesn't have hydrogen bonding. It only has London dispersion forces, which is the weakest force of attraction between molecules. Okay, now on the next part where you had to draw some pictures, let's make sure we got our pictures drawn appropriately. Okay, can you guys tell me why I made magnesium smaller than chlorine? Look at where they're placed on the periodic table. Do you see where magnesium is? Now, magnesium as an ion, what approximate size would it have? Give me an element that would appropriate its size. It loses 2 electrons, right? So now it has the same number of electrons as what? Neon, that's right. So it's going to have the approximate size of neon. Okay, now look at chlorine. Chlorine as an ion has gained an electron. So what's its size going to be like? Very good, Yibo. So you're comparing neon to argon in terms of size. And hopefully at this point, you know, as you go down the periodic table, down a group, the size gets bigger. It's like a snowman. Okay, so magnesium would be the smaller ion and chlorine would be the larger. Now, if you don't have your water molecules oriented properly, do so now. The Mickey Mouse ears go toward the chlorine with the negative charge. Eli, do you have this drawn? I drew my little salt down at the bottom, and then I drew each one of the ions with the proper orientation of water around them. So notice that the oxygen end of water would be surrounding that positive charge, the magnesium. I'll just color it that color. Here we go. And hopefully we've drawn enough of these that you may have to draw one on your AP test. I'm just going to, yes, I'm recording right now. I hope I am. If I'm not, I'm going to be very sad. Yeah. Yes, it says recording. Unless I didn't share my screen. Did I share my screen? Oh my gosh, I'm going to be so mad if I didn't.
I hope you did.
Well, I'll just re-record it if I didn't.
What?
Okay, I bet I haven't been sharing my screen, so people are like, oh well, I may just have to record the first part and do 2 videos in there. Okay, are we good with this part? Do you have any questions over you drawing stuff? Let's look at the next one on number 2. You had to draw the lone pairs of electrons on the structure, show the dipole-dipole interactions between water and the glycerol molecules shown below. Make sure you show examples of the hydrogen and oxygen ends of the water. So, guys, oxygen is always going to have, I did not put enough electrons in there. Because look, it's the way it is bonded to that. Oxygen's got to have 8. So, can you see that?
Wouldn't it have like 2 sheds be sharing 2 with the hydrogen?
With the hydrogen? Oh, there we go. Thank you, Alex. I didn't see the hydrogen off there, apparently, when I'm talking about it this time. That's why I didn't put them on there. Good job, man.
Thank you.
I guess I was just ignoring it. There we go. Okay, so oxygen's got to have 8. So you've got to show your 2 pairs of electrons on each oxygen. Are we cool with why I have the water molecule oriented the way I have it oriented? The hydrogens are going to be attracted to the negative electrons on the oxygen. Okay, and then over here I just showed the water molecules would be more oriented this way because the hydrogen part of that molecule is going to be more positive. Okay, and then on this number 3, it says show the dipole-dipole attractions between water and the amino acid molecule shown below. Make sure to show the water attracted to both functional groups. But there are actually 3 functional groups on here. Well, actually, I'll take that back. They're saying this is a functional group right here with the carbon double bonded to the oxygen. And then you've got this part. And then your other functional group is with the nitrogen on it. So you needed to put 1 lone pair on the nitrogen, and you needed to put 2 lone pairs on each of the oxygen. They're just trying to make sure everybody's got 8, except for hydrogen, right?
Because hydrogen doesn't need 8.
That's right. Remember, hydrogen's terminal. Are we good with that one? The water molecules, are you cool with the way the water molecules are oriented?
2, 4, 8.
And I tried to show, my pen was kind of skippy and didn't do very well, but these should be dotted lines, remember. When you show interactions, they're not straight lines, they're dotted lines, okay? So dipole-dipole, London dispersion, hydrogen bonding, that's all dotted lines between your molecules. Are we good with this page? Okay, I heard no protest. Let's move on then. Okay, so hopefully you have seen this graph multiple times. In fact, didn't we just do something with this the other day? Or maybe I'm thinking we've had those, haven't we? Okay, so this part, number 1 would represent our solid. Number 2 is representing where we're changing our solid to a liquid. So this would be the melting freezing point, depending on which direction you're looking at this. So if we're looking at it from left to right, that's your melting. Number 3 would represent your liquid. And what does number 4 represent? Liquid to gas, so that's your vaporization. And then number 5 is going to represent all gas. Okay, all gas up there. So I'm not going to go through all of these to show you every single possible answer, but let's look at B. It says for each segment, indicate whether added heat is being used to break intermolecular forces or increase the kinetic energy. Where are you breaking intermolecular forces?
At the phase changes.
At the phase changes, that's exactly right. So flat lines, that's where you're overcoming intermolecular forces. And I didn't like that word break because the better word, because I don't want you to confuse that with a bond breaking. You're not breaking bonds, you're overcoming forces. You're pulling these molecules apart from each other, not literally breaking a bond. Okay? It says C is, I think, a typo or a trick question. It says, why does segment 2 require more energy than segment 4? Well, if you look at the lines, look at segment 2. Yeah, it's actually required less heat, right? If you look at your x-axis versus number 4, segment 4, that's longer. So I think that this is either a typo or it's a trick question. So it actually doesn't. Segment 4 requires more energy than segment 2. And think about what the molecules are doing at each one of those segments. In segment 1, they're going from a solid to a liquid. Are the particles still touching? Yes. In segment 4, they're going from a liquid to a gas. Are the particles still touching when they make that transformation? No, gas particles aren't touching each other anymore. So you have to completely overcome that force of attraction between them. Okay, bless you, Tyler. Go get you a drink of water if you need one. Okay, so looks like that's as far as I got. So let's answer some questions together. Which constants would be required to calculate the heat involved for each segment of the curve? Okay, so on number 2, you're going to need the delta H of fusion. That's a constant. On number 4, you're going to need the delta H of vaporization. And all you have to do on those, it says which constants would be required. And then on segment 1, 3, and 5, you're going to need the specific heat of each one of those. So you're going to need the specific heat on section 1 of ice. On number 3, you're going to need the specific heat of water, like liquid water. And then on section 5, you would need the specific heat of vapor, water vapor.
What is number 2? Oh, that's sorry, what is that?
Whenever you're looking at,
The H something.
oh, the heat of fusion. Yeah, the enthalpy of fusion. And number 4 would be the enthalpy of vaporization. So those are constant values, guys. And so just remember, whenever you're dealing with these 3 segments, 1, 3, and 5, to find your heat energy, it would be Q is equal to what? What is that little formula? MCAT. There you go. Q is equal to MCAT to find that. And then you would actually have to have specific heat values for each one of those to calculate it. And whenever you're dealing with how much heat energy it takes for 2 and 4, you don't have a change in temperature, so it would just be the heat of fusion times the mass, the heat of vaporization times the mass, okay? Because delta T didn't change. All right, let's look at this Boltzmann-Helmholtz curve, which is what this thing is. I think we looked at this not too long ago, maybe. I may be running my pre-AP class. You do remember this or you don't? Okay, so let's talk about it. Okay, so one of the things you need to understand about this curve is the area under the curve represents the same number of particles, okay? Look at your x-axis, look at your y-axis. So on the x, it says speed. On the y, that says, somebody read that for me that has better eyeballs than I have. Okay, so proportion of particles. So, but the 2 areas represent the same number of particles. So if we said both of these represent 100% of particles, okay? If you look at these, which of these, if we said, okay, one of these represents a cold temperature, Sawyer Wyatt, and one of these represents a hot temperature. Which one would you think represents a cold temperature? I'm just going to outline this one in dark. So cold temperature, which one? You are? Okay, look at speed.
Slow.
Which one's slower? Are you sure? See, what this is doing is it's showing more particles are moving faster. See, you've got, look at some of your particles. They're getting all the way up to 1100 or 1200. Okay, the top of your particles here is right here. So you've got more particles with the dark line that are moving faster. It's like it'll trick your brain if you don't understand this graph. Okay, because you'll be like, oh, it looks like this one is going to be the higher temperature and the dark one's going to be lower temperature. It's the opposite. You have to look at what's on the x-axis. More particles are moving faster. It flattens this graph out. And so if I really wanted to show that particles are moving faster, I'd put another one on here. You see that one? And we could even say that represents a much, much higher temperature. Okay? Okay, so then it says the graph shows the distribution of molecular speeds for samples of carbon dioxide and nitrogen at the same temperature. So which ones would be moving faster? They're both at the same temperature, so they have the same kinetic energy. But one of these molecules is moving faster than the other one, the average speed. So N2 is moving faster. How do you know that, Alex? Because it's smaller and it weighs less. That's right. So you would actually have to look at the molar masses. Carbon dioxide weighs 44 grams per mole. Nitrogen weighs 28 grams per mole. So smaller gases move faster. That's right. So this one would represent the N2 and this one would represent the CO2. Okay, and then it says sketch a curve expected for Ne. Oh, I think I just did. Ne is a much smaller gas. Its molar mass is how much over there? Can y'all see that one? 20.1. Okay, so Ne, 20.1, and maybe I didn't do a great job, but we can call this one Ne, okay, because it's going to be moving faster. So that would flatten out. All right, now on number 6, let's see what you've labeled. I've got all these gas laws up here because it's what we're talking about in my pre-AP class, so you could have used that to your advantage there. The relationships that we have are between pressure, volume, temperature, and number of moles, okay? What is the only relationship that as one goes up, the other one goes down? Pressure versus volume, that's right. So that's going to be this one, and that's going to be Boyle's law. As pressure, or let's say as volume increases, pressure is going to decrease. And so this is Boyle's. P1 B1 equals P2 V2. I know it's been a while since you guys have talked about that, but just knowing the relationships. And then you can label the rest of these relationships any way you want. I'll put temperature on the bottom for those. So if I did temperature versus pressure, I could see that. So the gas law, P1 over T1 equals P2 over T2. Do you remember whose gas law that is? I'm going to tell y'all probably, and I hope this is a non-offensive way. Well, it probably is offensive to somebody, but I always remember this one as Gay-Lussac's gas law because it's gay and there's sometimes pressure that goes along with that decision. I don't know. That's just how I remember it. So it's the Gay-Lussac gas law. And I really hope that didn't offend anyone. I wasn't. That's just what my mind was thinking about. Okay, volume versus temperature. So you have V1 over T1 equals V2 over T2. And that would be Charles's law. And then we could relate number of moles to other stuff too, couldn't we? We could relate it to temperature. We could relate it to volume. So let's pick something for number of moles. What do y'all want to relate number of moles to? To temperature. Well, I don't know that that's actually true, because if you look at PV equals nRT, temperature and number of moles are on the same side of the equation, so they would actually be inversely proportional. So N would be either directly proportional to either pressure or volume. Pressure. Okay, so pressure versus number of moles. And so if you were looking at that, you would say P1 over N1 equals P2 over N2. And when you relate pressure to number of moles, that's Avogadro's law. Avogadro. But to be quite honest with you, here's your relationship that has all of them in it. And if you think about, if you divide any two variables on the same side of the equation, that's a directly proportional relationship. So like if you had to move N over here, it would be PV over N equals RT. Do you see how that number of moles would be directly proportional to pressure and volume? It's a division problem. All right, moving right along. Okay, so number 7, we're talking about gases. Which gas has the greatest velocity? I think we can figure that one out. Which one would have the greatest velocity? They're all at the same temperature. Helium, nitrogen, or argon? Helium. Okay, I'll let you go back and justify. Assuming the mass of the empty containers are the same, which cylinder would have the greatest mass? Justify your answer. So we have them all in the same volume. They would be at the same temperature, therefore they're going to be at the same pressure, but one of them is going to be heavier than the other one. Argon. Okay. Which gas has the greatest kinetic energy? They are the same. Why are they all the same?
It's the same temperature.
They are at the same temperature. That's right. Okay. So was that a trick question? I don't know. That could be a question that's asked. Okay. I've seen that one asked.
Still makes it.
I guess it could be a trick question. Eli Manning. Well, what's your name? Eli. I'm just going to make up a name for you. Eli Manning. All right. Eli Perrin. Wakey, wakey. Yeah, this is 4th grade. We should be filling this out.
I'm doing it.
Good. Okay. Same. Okay. Because at same temp. We got to speed it up, though, because we're only on page 5. I think I made y'all to 11. I don't think I copied the last page for y'all. Yeah. Okay. So number 8 is all about this solubility curve that we see here. Okay. It's not, let's just look at what we've got on here. Okay. And I'm not going to, basically I'm maybe answer one question, then I'll let you go back and finish the questions on it. If you look at all of these, do you notice a trend with most of these solids? They're all increasing with increasing temperature. So the solubility has a tendency to increase with increasing temperature when you're dealing with solids. Now, there's one that doesn't. This one actually, that's right. So this probably has a delta H that is negative, I bet. The rest of those would have a delta H that's positive because you put in heat energy, it causes it to break apart, right? So that would be, all those are going to have a positive delta H, but the rest, that one is going to have a negative delta H. Okay, so what forces of attraction are broken and what are formed during the dissolving processes for substances formed, which requires energy? Guys, this is just like this question, number 1. When you dissolve an ionic compound, this is what's happening right here. So what are you having to overcome? What forces? That is true, but these intermolecular forces, this is an ionic compound. So you are literally having to break ionic bonds when you pull those ions away from each other. And I thought I heard somebody say Coulombic forces. Did I hear that? Definitely not. Okay, but these would be ionic forces because you have positives and negatives. Would they not be Coulombic forces? Coulombic forces, okay, because you've got positives and negatives that are attracted to each other. So when we talk about what's happening with this, it says what forces of attraction are broken. So we would say ionic bonds are broken, which we could also call those Coulombic forces. It's on the board. Look, in big letters. Coulombic forces. Right. Okay, and then what else has to be overcome? Doesn't water have to like separate itself because it's got to overcome, because it's got to get stuff in between it, right? It's got to get the ions in between it. So what forces of attraction are you pulling apart when you pull water molecules away from it? Hydrogen bonding. So hydrogen bonding has to be overcome. Now, we're going to put these two substances together. So we've got an ion versus a water molecule. What forces of attraction? Just think about what you got. You got an ion, right? And what does water have? Hydrogen bonding only with itself. So it's a polar molecule, right? What dipole? That's exactly right. So the forces of attraction that are formed during the dissolving process would be ion dipole forces. You have to just think about, well, what two things are being attracted to each other? An ion to a polar molecule, that's called an ion dipole force. Okay. All right, let's do maybe one of these. I'm going to do letter D. Okay, a solution is made using 70 grams of lead 2 nitrate at 40 degrees Celsius. So find lead 2 nitrate on your little graph. Find it, find it, find it. Where's lead 2 nitrate? There it is. Good job. Okay, it's at 40 degrees Celsius. So we go to 40 and we read the graph. So I'm dotting up to that. Boom. Okay, and it says a solution is made using 70 grams. Well, 70 grams doesn't fall on my dot. So I've got at 40 degrees Celsius, I can put more than 70 grams. It looks like I can put about 76 grams in there. Okay, so about 76 grams will go in. It says if a crystal of lead 2 nitrate were added to solution, what would you expect to see? So far you've got 70 grams in there. Can you put some more in there?
Yep.
Yeah, you can put some more in there. So what would you expect to see? That's correct, the crystal to dissolve. Okay, justify your answer. Well, I think we just talked about it, but I'll let you go back and think that through. So that's just how you read the graph. Now, here's one thing it's going to talk to you about supersaturated versus unsaturated or saturated. The line is saturated, okay? So anywhere you're reading on that line, so if I'm looking at 40 degrees for lead nitrate, I can get 76 grams in there. That's saturated. If it's below 76, that would be unsaturated. Good, Alex. And if it's above 76, it would be supersaturated. Okay, that's how you're going to interpret that graph. Okay, so I'm not going to do any more of those. I think you can figure those out. Read your graph. Okay. All right, next page. Now, this is some kinetic stuff. So this is one graph that we definitely need to make sure that we review and understand because we've seen this one a lot, okay? So let's kind of do a little writing on this. Okay, I'm just going to kind of, that's a terrible line, but let's see if I can straighten it out there. There we go. Okay, now this little part of the curve, what does that represent for any chemical reaction? This part right here.
The beginning.
The beginning. And so what do we have at the beginning of a chemical reaction? What do we call those things that we start? Reactants. So if you look over here, it says circle the energy values that change upon the addition of well, let's label everything, okay? So these are going to be our reactants. Where are our products going to be located? At the end. So there are products. And so the difference between reactants to products, what do we call that? Nope. It is energy. It is delta H. And that is the enthalpy of a reaction. Delta H is enthalpy. It has the H in the word, enthalpy. Okay? So the difference between reactants and products is delta H. Now, right here, the reactants have to reach this little peak of energy before they can ever become products. And somebody already said that. What is that? That's activation energy. So label that E sub A. That's your activation energy. The peak is E sub A. So I just drew it down because it goes from reactants to the top And so if you looked at numbers over here on the side of this graph on the y-axis, then you could actually measure what is that activation energy if it had numbers, okay? All right, so in this first one, this says, sketch the effect of adding a catalyst on the potential energy. Now, I think I told a few people the other day, what does it do? Say again. It lowers that. It lowers what? The activation energy. So we're going to sketch it. It does not change where the products are. It does not change where the reactants are. It just simply lowers the activation energy. So I'm going to label that E sub A with a catalyst. And what a catalyst does is it provides an alternate pathway for the reaction to happen. Okay? Did I show you guys the video how to get a date for the dance?
Nope.
Dang it, I need to show y'all that. Okay, I will. Okay, we need 5 minutes. Okay, we need 5 minutes. We need 5 minutes. Okay, so let's look at the next graph. The graph below shows the distribution of the fraction of collision versus kinetic energy. This is very similar to the Boltzmann-Helmholtz curve that we saw a few minutes ago. The one where you had to draw helium on there, flatten it out. It looks similar to that. Okay, so this line right here represents the activation energy. Where are the only collisions that are going to cause a reaction to occur? Could you shade that area? That's exactly right. Shade that area. Those are the only collisions that have enough energy to undergo a reaction after the activation energy. Particles have to collide in order to react. They have to collide with enough force in order to break bonds. If they don't collide with enough force, they're not going to react. Okay? All right. Real quickly, I'm going to talk about this one because I don't think we've talked about this. These two graphs represent a two-step reaction. Okay? It's called a mechanism. And if you look at it, we're just going to let's clean this up a little bit. Okay, let's put some axes on here. That's not very good, but so label R for reactants, P for products. R for reactants, P for products. My lines aren't very straight. Okay, I want you to draw a line underneath your reactants to your products, and so this would represent delta H right there. Reactants to products on this one over here. Let's move this out of the way. There's your delta H. Right there. Do you see? You just draw a line under your reactants. So it's the distance from reactants to products. It's your delta H. So the question, you have to match some stuff on this. Okay? Now, a slow step in a reaction is going to take more activation energy. So these are two-step reactions. That's why we have two peaks. So this is representing activation energy 1 for the first step in the reaction. And this is representing activation energy as well, but it's for the second step. So in that first little graph that we see, can you tell me which step would be the slow step in the reaction? E sub 1, that's right, because it requires more activation energy. Okay, so that would be our slow step. And then in this reaction, notice again, this is activation energy 1, and this line from reactants, actually, this would be from here to here. That would be activation energy 2. Which step is the slow step in this reaction? EA2, that's the slow step. So the second step is a slow step. That's how you interpret those graphs, okay? Now, these are called, anytime you have a reaction that has multiple steps, each step is called, we call that a mechanism. Like, how does this reaction actually work? Here's the mechanism for the reaction, okay? So that's some kinetic stuff that we just kind of ran out of time to talk about. All right, moving on. So can you identify these now that you've got a little background information on it? Okay, good. All right, let's look at more kinetic stuff. I think you can do this from your stuff from the other day, so I'm not going to do this for you. This is chapter what, 12? Yeah, you guys drew these, so y'all shouldn't need my help on this part, okay? All right, so you got to label your axes, and there's a whole chart. I mean, there's like a chart that you guys had with these. All right. Okay, here's a concentration versus time graph, and your job is to decide, is this a 0, a first, or a second order? Now, the other day, we talked about a way you could tell that you had a 0, a first, or a second order graph. Which one of those has a half-life that's exactly the same amount of time every single time? First order, that's right. So let's look and see if we can tell our half-life. If I'm at 120 and then I drop it to half, how much time does that seem to be taking? It's 60. And then if I go half of that, which would be 30, is that the same amount of time? It looks like it, doesn't it? Can you look down here? Doesn't that look approximately like that's the same distance? And if I go 30 to 15, let's just do 80 to 40. If I'm at 80 and I drop it to 40, I don't know, 80, here's my time, to 40. Guys, that looks like it's the same increment every time. Okay, so that's how you determine if it's a first order reaction. If it has the exact same time increment, it's a first order. So I would say this one is a first order. It says the graph shows the change in concentration versus time. Explain how this graph could be used to determine whether the order is 0, first, or second. You must include all 3 possibilities in your answer. So a first order is the only one that has exactly the same time increment for each of the half-lives. Do you remember about a 0 order? A 0 order wouldn't even look like that. If you look at time versus concentration, what is a 0 order going to look like? Straight line, that's right. Okay, and so you could talk about that in your answer. And then if you're looking at a second order rate law, it doubles, right? So this really goes down fast. It kind of looks something like that, although I kind of did a bad drawing of that. And so on this one, you start out with the half-life time being really fast, and then it goes longer, right? Okay. All right, equilibrium. Do you guys need any help on this stuff? Okay, so let's talk about where we're starting. Okay, so in graph A, the point that I just labeled, what would that represent? Reactants or products? Reactants or products? If I'm starting at 0, wouldn't that represent a product? Reactants would be up here, right? The axis is not labeled, but I just said, what would this represent if I put this here? This would represent your reactants because you're starting with some. Okay? This would represent your products because you're starting with 0. So your reactants are going to decrease over time. Go with me on that. And your products would do what over time? Increase until they reached a point of, what is this called? Equilibrium. So now, can you see that this is going to be reactants? Those are going to be products. Reactants, products. Reactants, products. Reactants, products. Reactants, products. Where they flatline. So equilibrium is always when they flatline. Okay, that's once you've reached equilibrium, the flatline. Now, does that mean that reactants are equal to products? Heck no. In fact, I don't think that reactants are equal to products in any of these, are they?
Only when the lines cross.
Only when the lines cross, that's right. So at that point, reactants were equal to products, but then you end. That's right. Now, just remember, by definition, equilibrium is the place where the forward rate of the reaction is equal to the reverse rate of the reaction. That's what equilibrium is, okay? It's all about rates and when their values are equal. Okay, so thermodynamically favorable reaction. Goodness, let's see, what are we doing here? Non-thermodynamically favorable. It's time for the video. Okay, yeah, let's Now, guys, do go back and answer this acid base thing. Okay, that's real crucial. Yes, we can do that. And if I'm not here, because I hope to be at a ball game on Friday, I really do.
Have fun.
I'm just looking at you. We got to win tomorrow.
What is Friday's time?
Actually, I don't know. I might be able to be here for Friday. Do we know what time Friday might be played? I don't know. It just depends. 12. Ooh.
What is
I mean, you
Friday?
I'd be rushing it.
You can always record a video
I know. That's what I'll do for you guys. Okay. All right. So
and then have fun.
real quick, let's watch this video. We want to watch how to get a date for a dance.
Have fun as a gamer.
Thank you. A dance. This is it right here. Okay, guys. It's only 4 minutes and 56 seconds long. And so, but we got to watch the whole thing because it's really good. Oh, you know what? I probably need to go play it over there because y'all aren't going to be able to